In this video, I will introduce what is called the reconstruction problem. So we'll start here by connecting this back to automorphisms of graphs. So if U and V are similar vertices, so if there's some automorphism that takes U to V in a graph, then certainly it would be the case that if I delete U from G, that'll be isomorphic to when I delete V from G, if they're similar vertices. Get the same thing. However, the converse is not necessarily true. So for example, consider this graph I have here. If I delete U, if I do G minus U here, what'll I end up with? I'll end up with this edge by itself. And what'll be left? I'll have this triangle with this sort of dongle coming off of it. So I'll have something isomorphic to this graph. So that's G minus U. And let's see what happens when I do G minus V. If I delete V here, well, I'll be left with this edge. And then I'll have this triangle with this path of length 2 coming off of it. So that is, I end up with the same graph. So the converse of the statement is not necessarily true. So what this is sort of getting at is how can I determine what a graph is by looking at its vertex-deleted subgraphs, or at least suggest a route to explore in the world of graphs, which is to look at vertex-deleted subgraphs. If we know that two vertices are similar, we know that the vertex-deleted subgraphs, G minus U and G minus V, must be the same, but the converse is not necessarily true. Okay, so where do we go from here in this sort of exploration? Well, let's suppose we have two graphs, G and H, of the same order, such that G minus V is congruent to, is isomorphic to H minus U for some vertex V and some vertex U in H. Do we know that G is isomorphic to H? Well, I claim no, we don't. And I'll give you an example of this. So let's suppose we have, let's say G is the following graph. And H is this graph. So they're both the same order, same size. But if I say remove this vertex from U and this vertex from H, so I'll call this one, what am I calling this one? I'm calling this one V and I'm calling this one U. Then G minus V will be isomorphic to the path of order 4. And same thing for H. H minus U is isomorphic again to the path of order 4. So, all right, so this says if I just pick any two, or if I pick any vertex from G and any vertex from H, and I look at those vertex-deleted subgraphs, they can be isomorphic, and the original graphs are not isomorphic, right? Not isomorphic, but these two are isomorphic to each other. All right, so maybe this isn't enough information. Maybe it's not enough information to just have one vertex-deleted subgraph. So this sort of suggests, trying out something new here. I don't know if it's going to work very well. So this suggests something else to try. Sorry, this is not looking great. All right, so this suggests something else to try, and that is, well, what if we looked at the collection of all vertex-deleted subgraphs? So that is, so let's say my graph G has vertices U1 through UN. My graph H has vertices V1 through Vn, so same order again. And what if it's the case that G minus Ui is isomorphic to H minus Vi for each of the vertices? Is it then true? Does it then follow that G is isomorphic to H? In other words, do the vertex-deleted subgraphs of G completely determine G? Or is it possible that just by looking at the vertex deleted subgraphs that I could end up with two different graphs? So that's the question. We call a graph, so all right, so when you have a question like this, usually you give a name to the thing you're looking at. We call a graph G if it has this property, if its vertex deleted subgraphs completely determine it, we call it reconstructible. So a little bit more specifically, we say a graph is reconstructible if for every graph H with vertices U1 through UN, having the property that all of its vertex deleted subgraphs are isomorphic to G's vertex deleted subgraphs for each I, that implies that G is isomorphic to H. Right? This is what it means to be completely determined by your vertex deleted subgraphs. So that's the question. Is every graph reconstructible? So let's just take a look at what exactly I mean by this. So let's consider these vertex deleted subgraphs of this graph G, or of a graph G, right? It's possible we could get a couple graphs out. And I'll call these G sub I, where G sub I is G minus V sub I. So here our vertex set of G, we're sort of assuming is V1, V2 through Vn. And we're going to let Gi be G minus Vi for each. So we're looking at a graph of order 6 here. We're given 6 vertex deleted subgraphs. And then what do the vertex deleted subgraphs look like? Well, I'm given that G1, G2, and G3 all look like this. And G4, G5, and G6 all look like this. So this does tell me there's a good deal of symmetry going on with the graph. And the question is, so one question is, can we determine G from this? And is there another graph? If we can determine one graph that has these as its vertex deleted subgraphs, is it possible that there's another graph with these as its vertex deleted subgraphs? So, all right, we're going to get more into problems like this in the next video. What I'll say now is yes, these vertex deleted subgraphs completely determine G. So one way we'll do this is we can use these vertex deleted subgraphs to tell us how many edges are in the original graph. So it can tell us the size of the original graph G, and certainly it tells us the order of G. So that's one thing we can gather from these vertex deleted subgraphs, is that the order is 6, since we have 6 vertex deleted subgraphs. We'll prove this in a bit, but I can also determine the size of G. So let's say size of G is M. Then M, I can find M by adding up the size. So we'll say size of G sub I, we'll call it M sub I. Then in general, if I add up the size of the M sub i's, I equal 1 to 6 here, and divide that result by n minus 2, so that would be 6 minus 2 here, that'll tell me the size of the original graph. So maybe this is a little bit of a mystery. I'll let you think about it for a while, and then we'll prove it in a later video. So I'll let you kind of, just think about that. So let's see, 1, 2, 3, 4, 5. Each of these is size 5. I have 3 of them, so that's what, 15. Contribution from those vertex deleted subgraphs. 1, 2, 3. Each of these has 3 edges in it. So that's another 9 from those vertex deleted subgraphs. N is 6, so that's divided by 4. This tells me that the original graph must have also size 6. So order is the same as the size. That means it must be a unicyclic graph. So I'm able to surmise that much. And so now now that I know the size of G, I can actually determine the degrees of each vertex, right? If G sub 1 looks like this, which is 1, 2, 3, 4, 5, has size 5, and I know there's a total of 6 edges in the original graph, well, that means that my vertex 1, so this tells me that the degree of V1 must be 1. And same thing for V2 and V3. Those degrees must all be 1 in order for the original graph to have size 6. And then I can also surmise the degrees of V sub 4 and 2, 3. That means it must be degree 3. Degree of V sub 5 is 3. Degree of V sub 6 is also 3. So I'm able to, I have some good information here from the vertex deleted subgraphs. We determined its order, its size, and I guess if you want the degree sequence of the graph. From here, we can start doing some trial and error investigation on what G might be. So what I can do is I can look at, say, what is, looking at these vertices of degree 1, well, how can I put a vertex of degree 1 in here? So I'll take that graph. I want to add in V1 into this. So what if and I know that degree of V1 is 1, so what if I say put it here? Well, then if I deleted this vertex here, it would follow that one of the vertex deleted subgraphs would be this triangle with an edge, with a pendant edge, and then an isolated vertex, but I don't see that. And so that can't possibly be the case. So this is what I mean by trial and error. You can kind of try putting this V1 in there. I could say put the V1 like that. But again, if I removed this vertex now, I'd be left with just a path of length 2 and then and then 2 isolated vertices. Well, I know that's not one of my vertex deleted subgraphs. And so you can kind of go through all these possible cases and see that, well, the only way to do this is if V1 is attached to this as a pendant edge coming off of the triangle. And then, so that would be my V1. And if I let V2 be this vertex, that'll work. If I delete V2, I'll end up with this graph. If V3 is this one, I'll end up with this graph again. And then we can check now, if I delete, say, this vertex here, I'll end up with a P4 and an isolated vertex. And that'll be true for each one of these vertices here. So I can call these however I want. How about V4, V5, V6? And so notice here, these vertex deleted subgraphs, we were able to get all of this information and then through trial and error find out that the only way to form G from this vertex deleted subgraphs was to have this as G. That these vertex deleted subgraphs uniquely determined G. So that's what we mean by uniquely determine. And so this question, again, I'll remind you of the question. Right, we want to know, is every graph reconstructible? Well, that's a tough question. This is a conjecture, reconstruction conjecture. Every graph of order at least 3 is reconstructible. And the reconstructible problem then is to determine the truth value of the reconstruction conjecture. So why do we need order at least 3 here? Well, I can think of 2 graphs of order 2 that are not reconstructible. So what does it mean to be not reconstructible? It means there's 2 graphs that have the same list of vertex deleted subgraphs. So I'll let G1, or actually I'll use maybe the same notation as before. I'll let G be K2, and I'll let H be the empty graph, K2 complement. Well, G, its vertex deleted subgraphs would be isolated vertex and an isolated vertex. And then H, its vertex deleted subgraphs would be isolated vertex and isolated vertex, right? This would be like G1, G2. This would be H1, H2. And so we have the case that G1 is isomorphic to H1. G2 is isomorphic to H2, but G is not isomorphic to H. So these 2 graphs are not reconstructible. And the claim, or the conjecture at least, is that these are the only 2 graphs that are not reconstructible. That is, every graph of order at least 3 is reconstructible. So a little bit of work that's been done on this problem. We do know that every graph of order up to 12, at most 12, is reconstructible. Now, there's also a lot of other work. I'm going to go ahead and delete this for a second. There's also other work that's been done on this. So what we're mainly going to focus on here is two sorts of ways to go off of this reconstruction problem. So one is given the list, or we'll call it a deck, because we'll think of the vertex deleted subgraphs as cards. So given the list or deck of vertex deleted subgraphs, we want to be able to determine the original graph G, like we did before. So I want you to be able to do this for certain decks, certain lists of vertex deleted subgraphs. And then the other thing we're going to want to focus on, and this will actually help us solve this problem, is to investigate what are called recognizable properties. So for instance, we were able to determine in the last that example we looked at, where we looked at the vertex deleted subgraphs, we were able to determine the order, we were able to determine the size, and we were able to determine the degree sequence of the original graph. Question is, so we would call each of those properties recognizable. That is, given the list of vertex deleted subgraphs, I can figure out exactly what this parameter is for the original graph. So yeah, these three properties are all recognizable, but what about other things? What about like bipartite or connectedness? Can we tell if the graph is connected or not? There are all sorts of graphical properties now that we can ask if they are recognizable. And so that's how the rest of these videos are going to go. We're going to investigate these two problems and see how they relate to each other. All right, see you next time.